Okay, I've got a couple of point charges. One is a strength of plus Q. The other one is twice as strong, so strength of plus 2Q, and they're separated by a distance D. And I take the direction that goes from plus Q to plus 2Q to be the x-axis. The question we're going to ask in a couple examples here is, where could the electric field be zero if those are the two charges? The first point to make is that it can't be anywhere off of the x-axis. Because if I think about like a point up here, that's going to be repelled by the plus 2q, that's going to be repelled by the plus q. I add those two vectors together anywhere off the axis, above the x-axis, below the x-axis. I can't get those two to sum to zero because they can't be pointing in opposite directions and have the same strength. There's always going to be some residual in adding those two vectors together. So the only way I can get cancellation is going to be somewhere along the x-axis. And there are three domains to think about. I could be to the left of the plus q charge, I could be to the right of the plus 2q charge, or I could be in between the two charges. So let's go through and think about those individually. So the first case, I'm left of the plus q charge. Well, it's going to be repulsion from both of these, so their electric fields from each point charge are going to point to the left. So I can't have cancellation for x smaller than 0. And for a similar reason, I can't have cancellation for x bigger than d. Because for x bigger than d, it's repulsion from both charges. They're making electric fields that point to the right. And so there can't be cancellation because they point in the same direction. If I'm going to have cancellation, it's going to have to be somewhere along the x-axis between x equals 0 and x equals d. If these two charges were the same strength, then by symmetry, just right in the middle. There would be same strength charges, equal distance from each charge, therefore the net field is going to be 0 there. But they're not equal magnitude. This is the stronger charge. So intuitively, when we actually get an answer out of this, it should turn out that it is at a point that is closer to the weaker charge, because I'm trading off having a shorter distance in the 1 over r squared being compensated for with a weaker magnitude. So I'm going to label the point, let's call it x. Okay? And we're basically solving for x. What is that coordinate where the electric field equals 0? So principle of superposition. The electric field at the point x has two components. There's the component from the plus q charge. That's going to point to the right. So I'm going to have a plus kq. I'm a distance x away, so x squared. And then it points to the right, so plus x hat. The electric field caused by the plus 2q charge is going to point to the left. So I'm going to have a minus. It is 2kq x hat, and then how far away am I? Well, if this distance is d, the distance from here to there is going to be d minus x. So d minus x quantity squared. That equals 0. So I've got a plus kq over x squared, x hat direction, minus 2kq, d minus x quantity squared, x hat direction. All right. Now a lot of things are going to cancel out here. K is in both terms, Q is in both terms, and I can get rid of x hat. It's just telling me a direction. So I move the negative term to one side. I'm going to wind up with an equation that looks like 1 over x squared is going to equal 2 over the quantity d minus x squared. All right, so we're going to get everything that involves x on one side of the equation. So I can clear out this square. So I'll have a d minus x quantity squared for an x squared equals 2. I can clear out the square by taking the square root of both sides. D minus x over x will equal root 2. Now I want to get rid of this x in the denominator, so multiply both sides by x. D minus x will equal root 2x. Move this minus x to the other side. I do that by adding plus x to both sides. D will equal root 2x plus x, which I can write as x times 1 plus square root of 2. Now I'm ready to solve to get x in terms of d. X will be d over 1 plus root 2. So square root of 2 is bigger than 1, so this numerator or denominator is bigger than 2, and so in fact x is less than d over 2. So it will be closer to the weaker charge, as we had sort of intuited to begin with. Alright, so let's see what's different if I switch out one of these charges. So let's go through a similar example, a similar idea, where is the electric field equal to 0, except now the charge that's a distance d away is a minus 2q. Okay? And just as before, I can't have the electric field be 0 anywhere off of the x-axis. The last time we found that it was going to have a 0 in between the two charges, so let's think about that case first. If I'm somewhere between 0 and d, I'm going to be pushed to the right by the positive charge, and I'm going to be pulled to the right by the negative charge. So in between the two, I'm going to have an electric field that is going to always point to the right, can't go to 0. Alright, so let's think of the case where I'm along the x-axis, but I am to the right of x equals d. Well, in that scenario, I'm always going to be physically a smaller distance away from the stronger charge. So when I add those two together, even though the minus 2q is going to make an electric field that points to the left, and the plus q makes an electric field that points to the right, they have opposite directions. They're never going to be able to cancel, because I'm always going to be closer to the stronger charge. That one is always going to dominate. So the electric field can't be 0 anywhere for x greater than d. So the only place left is where x is to the left of 0, so x is smaller than 0. So somewhere along the x-axis here, I will be the right distance away that the larger distance to the stronger charge is compensated by a smaller distance to the weaker charge. And I can get the repulsion, which is going to point to the left from the positive charge, to cancel out the attraction pointing to the right from the negative charge. Alright, so let's write that out, and we have to be a little bit more careful this time. So our same idea is superposition of the electric field. It's going to give us 0. There are 2 point charges, so there will be 2 contributions in the sum. 0 is going to equal, it points to the left from the positive charge, so I have a minus k, q, x hat, and I'm going to actually write the distance to this point in question as the absolute value of x quantity squared, because I know it's going to have to be negative. And when I get the distance away from this charge, it's going to have to involve the absolute value, so I want to go ahead and solve for the absolute value of x here. All right? So everything will be in terms of the absolute value of x. And then when all the dust settles, we'll pick the proper sign for that gives us this value that's negative. All right. Attraction to the minus 2q is going to be an electric field that points to the right here at point x, and so that's going to give me a plus 2kq x hat, and then how far away am I from the minus 2q point charge? That's going to be a distance d plus the absolute value of x quantity squared. So that's why I wrote this in terms of the absolute value of x. That's what we're actually going to solve for. Alright, as before, much cancellation, k goes away, q goes away. We can get rid of the x hat by dotting both sides of the equation with an x hat. And we'll wind up with an equation for 1 over the absolute value of x quantity squared equals 2 over d plus absolute value of x quantity squared. Same as before, I want to get everything that's squared on one side so we can clear it. I have a d plus absolute value of x quantity squared for absolute value of x squared equals, 2. Then I'm going to take a square root of both sides. D plus absolute value of x over absolute value of x equals root 2. And then multiply both sides by absolute value of x. And then move the plus absolute value of x to the right-hand side by subtracting absolute value of x from both sides. So I'll wind up at d is going to equal root 2 absolute value of x minus the absolute value of x, and that's going to be absolute value of x times the quantity root 2 minus 1. All right. Solving for the absolute value of x is going to be d over the square root of 2 minus 1. And then out of the 2 possible signs for x, we want the one that corresponds to a negative value of x. Square root of 2 minus 1 is positive, d is positive, so what we want is the value minus d over the square root of 2 minus